This is the second lecture, and the title of the lecture is Signals and their Transformation. We are going to look at various kinds of signals in the continuous time domain as well as the discrete time domain. But first we look at some transformations. Let's consider a signal like this. And let's say this is x of t versus t. Naturally, this is a continuous time signal. Now, if I flip this signal, if I turn it over, or let's say if I wish to make x of minus t, and if this is 0, does the shape change? No, it doesn't change. On the other hand, suppose we have a signal like this. Let's say a signal like this, the red one, all right? Now, if this is, let's say, y of t, and we want to find out y of minus t, then y of minus t would be like this. Is that clear? Y of minus t would be flipped over. Now, this is called folding, all right, or reflection. Y of minus t is the reflection of y of t. Now, if you think y of t to be a tape recorded speech, then y of minus t represents the same tape run backwards. Is that clear? All right. This is called folding, or as I said, reflection. This is one kind of transformation that a signal can have. Now, the signal does not necessarily have to be continuous time. It could be discrete also. For example, I could have a signal like this. Which exists only at discrete instants of time, then its folded version or the reflected version would look like this. So whatever transformation I speak of with respect to continuous time domain signal also applies to discrete time domain signal. All right. After folding, let's look at scaling. That is, if the independent variable is scaled, that is, I have an x of t, a signal. As I said, it could be continuous time. If it is discrete time, then I shall write this simply as x of n. All right. Now, if I have a signal x of t and I want to scale the independent variable, that is, t I wish to change to alpha t, where alpha is a constant, then how does this signal change? Let's look at it like this. Once again, we take a very simple signal, let's say a triangular signal, which is like this. This is t and this is x of t, this is 0, and let's say this is plus 1 and this is minus 1. All right. Now suppose I transform small t into, let's say, twice t, let alpha be 2. That is, I wish to plot x of 2t. Now x of 2t would be 0 when 2t is equal to 1, plus 1 or minus 1, and therefore naturally the signal now shall look like this, where this value is half and this value is minus half. And as you see, x of 2t is a compressed version of x of t. This is called compression in time. Compression in time. This happens when t is multiplied by a constant which is greater than unity. In terms of, let's say, tape recorded signal, if the blue curve x of t is a tape recording of a speech, then x of 2t represents the same speech run at twice the speed, right? At twice the speed. On the other hand, if the constant alpha is less than 1, let's take another color. Let's say we want to plot x of t by 2. Then you see x of t by 2 would be 0 when t by 2 is equal to 1. In other words, the signal gets stretched in time. So this is t equal to 2 and this is t equal to minus 2. If the blue curve is a tape recorded speech, then the red one is the same speech run at half the speed, and therefore it is the stretched version. The whole process of transformation is known as scaling. Scaling can have two types of phenomena, namely there can be a compression in time or there can be a stretching in time, as we have illustrated. This is the second form of transformation. Next we look at a signal, let's say x of t, which is let's say like this. Let me use another color. Let's have a signal like this, and a signal which looks exactly the same, except that it's shifted either to the right or to the left. If I call this as x of t, and if this is 0 and this is, let's say, capital T, that, I'm sorry, not this point, let's say this point is capital T, then all that it means is that the time scale has been shifted. Time origin has been shifted from t equal to 0 to t equal to capital T, and therefore this new waveform which I obtain by shifting is simply x of t minus capital T. And the argument is absolutely clear that x of t minus t is this value, which if we say capital A, then x of t minus t is capital A when the argument is 0, that is small t equals cap T. This transformation of a signal where the shape of the signal does not change, it's only shifted either to the right or to the left. If I want a left shifted signal, then I shall have an expression like x of t plus cap T instead of minus cap T. The negative sign here indicates that it is a right shift, a positive sign indicates that it is a left shift. Now, the right shift, that is, if the new signal occurs after some time compared to the original signal, then obviously it is a delayed signal, delayed. On the other hand, if the signal is made to appear before the original signal, naturally this is an advanced signal, and therefore the general phenomenon of transformation is shifting or shift. Shifting can be of two types. It could be either advance or delay. Now, advancing a signal in real time is not possible. It is only possible if it is a recorded signal and you can handle the way you like. Delay is what can be achieved in practice, in real time. We next consider some types of signals. We go back to our triangular signal, which is very convenient to handle, and let's say this is the axis x of t versus t. If it is symmetrical about the origin, t equal to 0, and let's say this is capital T and this is minus capital T, then naturally if we flip it or we reflect it around the vertical axis, then there is no change. Such signals which with reflection or folding does not change, it retains its original shape. That is, if x of t is the same as x of minus t, then you call such a signal as an even signal, even. Alright, I could draw many other examples. Let me draw on the same figure another example of an even signal. I could have a signal like this and like this. This is also an even signal. But suppose I have it only on one side, that is, this side is absent, then it does not remain an even signal. An even signal is one which with folding or reflection does not change. X of t equals x of minus t, this is the definition of an even signal. On the other hand, if x of t is related to the folded version with a negative sign, then it is called an odd signal. I can draw a simple example of an odd signal like this. This is t, x of t, which is odd, and if x of t is, let's say, like this for t greater than 0 and it is odd, then it must go like this. If this is capital T, this is minus t. So x of t is equal to negative of x of minus t. You fold this and negate it, you will get exactly the same thing. Alright, this is called an odd signal. And of necessity, you see that an odd signal at t equal to 0, x of 0 is minus x of minus 0, but plus 0 and minus 0 are the same, and therefore of necessity an odd signal must vanish at its argument equal to 0. Is this point clear? An odd signal cannot have a non-zero value at its argument equal to 0. Alright. A general signal in general is neither even nor odd, and therefore a general signal, general x of t, can be written as an even part and an odd part. Any arbitrary signal can be broken up into its even part, even x of t, plus odd x of t. Alright. Because these are the two basic kinds of signals, and an arbitrary signal is a combination of the two. There are examples in the text which will demonstrate with pictures as to how. We will also work out in tutorial class. Now, if I negate time here, that is, if I fold this signal, this general signal, then x of minus t, well, if I change t to minus t in the even part, it does not change. I can write this as even part of x of minus t plus odd part of x of minus t, and because of the definition of evenness, this is the same as even part of x of t, whereas the odd part is the negative of odd part of x of t. This is by definition of evenness and oddness. And if I combine these two equations, 1 and 2, then you see that the even part of any signal x of t can be written as, if I add the two x of t and x of minus t, if I add the two, this and this, then the odd parts cancel and I get twice the even part, and therefore I divide by 2. On the other hand, if I wish to find out the odd part of x of t, then all that I have to do is to have a negative sign here. That is, subtract x of minus t from x of t, then you get twice odd x of t, and therefore odd x of t is equal to this. So we know how to find in general the even part of an arbitrary signal and the odd part of an arbitrary signal. All that you have to do is to apply the transformation of folding, add the 2, divide by 2 to get the even part, subtract x of minus t from x of t, divide by 2, you get the odd part. The evenness and oddness of a signal has great significance in the context of Fourier analysis, as you shall see later, and also any other analysis, if the signal is either even or odd, it greatly simplifies the analysis, and that's why we put emphasis on these two adjectives, namely even and odd. Next we consider another kind of signal, namely periodic signal. Whatever we are saying with respect to signal transformation or evenness, oddness or periodicity, although I am taking for simplicity a continuous time signal, the concepts are valid for discrete time signals also. And to be precise, we will define a periodic signal like this. If it is continuous time, then I will say x of t is periodic if and only if there exists a constant capital T such that x of t is equal to x of t small t plus cap T. This is the definition of a continuous time signal, continuous time periodic signal. For example, if I have a signal like this, a signal which repeats, this is x of t, which repeats at regular intervals of time, and this distance is capital T, then it is a periodic signal. Now, it is not necessary for periodicity for the signal to be continuous time. A discrete time signal can also be periodic, and if I have a discrete time signal, then it shall be considered periodic if and only if x of n, that is the symbol for a discrete time signal, where small n, as I had explained in the first lecture, is an integer variable. A discrete time signal is periodic if and only if x of n is equal to x of n plus some integer constant. That is the restriction. In the case of a continuous time domain, there is no constraint on capital T. Capital T could be an integer, could be a general number. It could be a fraction, it could have a characteristic, it could have a mantissa. Whereas in the case of a discrete time signal, this capital N must be an integer. This is the basic difference between a periodic continuous time signal and a periodic discrete time signal. This discrete time signal periodicity shall require a little more examination, closer examination, and we shall do that a little later. As far as the continuous time signal is concerned, x of t equal to x of t plus capital T. If this signal, if this continuous time signal is periodic, then isn't it true that x of t plus capital T must be the same as x of t plus 2t? Or x of t plus 3t and so on. That's how it becomes periodic. The pattern is repeated at regular intervals of time, and therefore we can say x of t is periodic if x of t is x of t plus mt, where m is an integer, an arbitrary integer. All right. Now the point is, what value of this constant shall we take in the definition? Well, you can use any value you like. It can be capital T, it can be 2t, it can be 3t. But obviously, there must exist a minimum for this t, for this signal to be periodic. And this minimum is called the period or the fundamental period. The adjective fundamental is usually omitted. We simply call it period. Period is equal to smallest, we will not use capital T now, we will say smallest alpha satisfying, period is defined as the smallest alpha satisfying x of t equal to x of t plus alpha. You see that alpha could be capital T or any integer multiple of capital T. The smallest alpha which satisfies this relation, we shall call it the fundamental period or simply the period. The period obviously has the dimensions of seconds. All right. If I take the reciprocal of the period, that is 1 by capital T, the dimension is second to the minus 1. Obviously, it determines the number of periods in 1 second. 1 by capital T is the period in seconds. Let's say 0.1. If capital T is 0.1, then in 1 second, how many periods occur? Obviously 10. And this is called the frequency f. 1 by capital T is the frequency f, and the unit is cycles per second, or simply to honor Heinrich Hertz, who first used this term frequency and used the unit cycles per second, we simply call it f Hertz. We will come back to this later on many occasions. So this is a periodic signal. In the case of a discrete time signal, the periodicity shall be a little more demanding, and as I said, the definition is okay. X of n is x of n plus capital N, where capital N is an integer, and capital N shall be equal to the period if this is the smallest value satisfying this relation. Capital N will be called the period or the fundamental period if capital N is the smallest integer which satisfies this relation, smallest integer which satisfies this relation. And in consonance with the continuous time definition of frequency, we can define a frequency here also as 1 by n, but this requires a closer examination, and we shall come back to this later. In tune with periodic signal, we next consider what is known as an exponential signal. And to be specific, we first consider continuous time exponential signals. A continuous time exponential signal is simply of the form some constant capital C, then exponential e to the power some constant a multiplied by t, where c and a can be real, can be positive, can be negative. They can also be complex. One of them, c can be real, a can be complex. Both can be complex, and it would be instructive to consider all these cases one by one. First, let us say c is real and a real and positive. C is real and a is real and positive. Then obviously a plot of this shall look like a growing curve. That is a curve which has an upward slope, a positive slope all the time. And if this is if this is t and t equal to 0, then obviously this value is equal to cap c, and as time proceeds it goes on increasing. A natural phenomenon could be the growth of population in the world, in particular in India. Well, it is known that population grows exponentially. So an example could be population growth. Suppose c is real and a is negative. A is also real and negative. Then a plot of this signal versus time, let me use some other color, time would be like this. A natural phenomenon that can be compared to this situation, this is t equal to 0, is, let's say, the real worth of a rupee. It goes down exponentially with the number of years. On more concrete terms, things which you are familiar with, let's say you have an RC circuit which is suddenly connected, now let's have it the other way around, a CR circuit instead of an RC circuit, and it is connected to a battery at t equal to 0, CR circuit. And if you look at the current, what is the initial value of the current? The battery divided by the resistance, E by R, and then this part is away, E by R, and then it decays exponentially according to E by R, e to the power minus t, small t, divided by cap t, where cap t is equal to CR. So the decay of current in an RC circuit excited by a battery is an exponential signal. It decays exponentially. Now let's consider a little more, let's consider a little more complicated cases. Namely, let's say C is real and A is purely imaginary. Let's say A is equal to j omega 0. That means a signal, for example, could be e to the power j omega 0 t. This is an exponential signal. And it should be obvious that this signal is periodic. To test whether this signal is periodic or not, what we do is we equate this to e to the power j omega 0. We increment small t by some constant, let's say capital T. Can this relation be satisfied? If it can be satisfied, that is, if you go back to the definition of a periodic signal, if there exists a capital T for which x of t equals x of small t plus capital T, then the signal is periodic. So, can we find a capital T which will satisfy this? Obviously, you see that this, if you simplify this, it becomes e to the power j omega 0 t multiplied by e to the j omega 0 capital T. And what we need is that this factor e to the j omega 0 t, this should be equal to 1. And obviously, this is equal to 1 if omega 0 t is equal to an integral number of 2 pi's, that is 2 pi m, let's say 2 pi m. Now, the smallest m e to the j omega 0 t, the smallest m shall define the period, that is the fundamental period. Fundamental period obviously is given by capital T. This is periodic if omega 0, capital T is 2 pi. So, capital T is 2 pi over omega 0. Alright. This is the period or fundamental period of the exponential signal, and the frequency f, which is 1 by t, is therefore omega 0 by 2 pi. A special case of the exponential, the complex exponential signal is the sinusoidal signal, which can be either cosine or sine. And you see that cosine or sine is simply, cosine is simply the real part of e to the j omega 0 t, and sine is simply the imaginary part of e to the j omega 0 t. Is this correct? Well, if it is to be correct, then you should write e to the j omega 0 t. Let me use another. E to the j omega 0 t you write as real part plus imaginary part. Is that how you should write it? J times, that is correct. And therefore, cosine omega 0 t and sine omega 0 t both are periodic signals with a period capital T, which is equal to 2 pi over omega 0. A general sinusoidal signal can be a combination of cosine and sine, and a general sinusoidal signal can be written in the form a cosine of omega 0 t plus, let's say, phi. And this, as you see, is a combination of sine and cosine. This contains cosine omega 0 t as well as sine omega 0 t, and if you plot this versus t, you will have a plot like this and so on, where this value at t equal to 0 is a cosine of phi, where the distance between two peaks shall be equal to capital T, and capital T is equal to 2 pi over omega 0. This is the general sinusoidal signal. Now, a sinusoidal signal, let's say e to the power j omega 0 t, if you have another signal x1 of t, let's say one of the signals is e to the j omega 0 t, if you have another signal x2 of t in which the power of e is simply multiplied by some constant m, where m is an integer. M is an integer. Then you see that the frequency of x1 and x2 are related by multiplication by an integer. For example, f1 is omega 0 by 2 pi. f1 is the frequency of x1 of t, and f2, the frequency of the second signal, is simply m omega 0 by 2 pi, which is equal to m times f1. That is, the frequency of the second signal is related to the frequency of the first signal by an integer multiplication. Such signals are called harmonically related. Harmonically related. x1 and x2 are harmonically related, and x2 is said to be the mth harmonic. x2 is the mth harmonic of x1. x1 is also called, if there are such harmonic signals, that if we consider a conglomeration or an assembly of signals which are harmonically related, then there exists a basic signal, that is a signal which has the minimum of all these frequencies. Suppose you have 1k, 2k, 3k. Suppose you have 3 signals which are of frequencies 1 kilohertz, 2 kilohertz and 3 kilohertz. Then the minimum frequency signal is called the fundamental, and all others are called harmonics. Fundamental frequency and all others are called harmonic frequencies. The definition, the origin of this term harmonic goes back to music. Musical tones are harmonically related to each other. Harmonic relation or harmonically related signals play an extremely important part in signals and systems analysis, and we shall see that Fourier analysis is basically finding the interplay or interaction between the harmonically related frequencies. Now, if you remember, we have been on the exponential signal, and we said it's in general of the form c e to the at. We considered c to be real so far. A could either be real, positive or negative. We have also considered A as purely imaginary. Suppose A is complex. Suppose A is sigma plus j omega sigma 0 plus j omega 0 t. Well, then obviously the signal can be written as c e to the power sigma 0 t. Now this defines the amplitude, and e to the power j omega 0 t, which is periodic. And if we take the real part or the imaginary part, we can make plots. For example, the real part of this signal shall be simply c e to the power, I beg your pardon, c e to the power sigma 0 t cosine of omega 0 t. Now, the plot of this shall depend on the sign of sigma 0. If sigma 0 is positive, then it would be a growing sinusoid. We are considering c e to the power sigma 0 t cosine of omega 0 t. Well, as t increases, the plot, if sigma 0 is greater than 0, then the plot shall be like this. It will grow with time. The amplitude will grow with time. On the other hand, if sigma 0 is negative, then it will go like this. It would be a decaying sinusoid like this. Sigma 0 is less than 0. If we know these basic considerations, then we can now treat the case where C as well as A are complex. Let's take the most general case. That is C is complex, let's say C1 plus C2, or we could write this as mod C in the polar form, thanks to Euler, e to the power j theta, let's say. Then you know magnitude C is square root C1 squared plus C2 squared, and theta is tangent inverse of C2 by C1. Alright, this is C, and let's say A is sigma 0 plus j omega 0. Then you can write the signal x of t, which is C e to the power at, as mod C e to the power sigma 0 t e to the power j omega 0 t plus theta. And you see that you can easily plot this real part and imaginary part separately, and it would either be both parts, both real and imaginary parts shall either be a growing exponential or a decaying exponential, depending on whether sigma 0 greater than 0, this is a growing exponential, sigma 0 less than 0 shall be a decaying exponential. And all that you see in communication signals, they are either growing or decaying, mostly decaying, and therefore one has to use many kinds of processing to be able to recover the original signal. Exponential signal is one of the elementary signals, that is one of the basic signals, and we are considering continuous time domain. Exponential is one of the basic signals. Two other basic signals which are of importance is the so-called unit step, and it is denoted by u of t and defined like this. It is 0 for t less than 0 and unity for t greater than 0. This is the definition of the unit step, and if you want to plot it, ut versus t, this is small u. The plot, obviously it is 0 for t less than 0, for t greater than 0 it is 1. At t equal to 0, the value is not determined because there is a discontinuity. At t equal to 0, the function changes from 0 to 1. So u of 0 is not defined. You shall see that in our later discussions. For our convenience, we shall define the value wherever it is convenient, and the consideration there would be not strictly mathematically true, but from engineering considerations. For engineers, anything that works is good enough, and a value, if we set a value for ut at t equal to 0 and it is adequate for the particular purpose, engineers accept it, mathematicians do not. The reason I mention this difference between engineers and mathematicians would be clear when you define the next elementary continuous time signal, which is called the unit impulse, and it is denoted by delta t. delta t cannot be defined by a value. Delta t is defined by an integral. The physical concept of delta t is that it exists only at t equal to 0. It does not exist anywhere else. The function is 0 everywhere except at t equal to 0, where it rises infinitely, that is, its amplitude is infinite. Obviously, there are some mathematical problems in the definition, and therefore what one does is one defines a unit impulse function delta t by an integral, that is delta t dt, which defines the area under the curve. Since the amplitude of delta t goes to infinity, we cannot define it in terms of an amplitude, and therefore what we do is we define it by its area. If we integrate from minus infinity to plus infinity, then this area is taken as 1. This is the definition of delta t. If this definition is correct, you see, in the conventional sense, the function delta t is not defined, cannot be defined. But if we take help of this integral, several interesting phenomena occur. Namely, suppose we integrate from minus infinity to, let's say, t, this function delta t dt. If you prefer the integrand, the variable of integration, you can define as tau instead of t. If this small t is less than 0, then the value of the integral shall be 0, because the function did have no chance to show its face, it didn't appear at all. On the other hand, if t is greater than 0, it is 1. We also make fine distinctions between how close t is to 0. So we say if t is less than or equal to 0 minus, that is, it has come very close to 0, but it has not quite reached 0. On the other hand, if t is greater than equal to 0 plus, that is, it has reached 0 and exceeds 0, then the value is unity. There are several other interesting phenomena, that is, minus infinity to t, the same integral delta tau d tau. If t is greater than 0, it is interesting to see that this is the same as u of t, the unit step function, because by definition and implication it is equal to 1 for all t greater than equal to 0 plus, and small t less than equal to 0 minus, it is 0. That is precisely the unit step, and therefore the integral of the delta function, the unit impulse, is the unit step. And if two functions are related by integration, they can also be related by differentiation, that is, dut dt must be equal to delta t. If this is true, then this must be true. That is, if you integrate, if you differentiate the unit step, then you should get the unit impulse function. Physically, it does make sense, because the unit step changes from 0 to 1 at t equal to 0. This is unit step ut, and the differentiation anywhere else than t equal to 0 is 0. ddt is 0 here, ddt is 0 here, because it's a constant. However, ddt is precisely, in the strict mathematical sense, is not defined at t equal to 0, because it is a discontinuity. differentiation is not possible at a discontinuity. However, if you see physically, it goes from 0 to a finite amplitude 1 in no time, 0 time, and therefore change of amplitude divided by change of time is infinity, and therefore it stands to reason. On the other hand, if instead of a unit step, it is, let's say, a step of magnitude k, then this amplitude shall be k, and the ddt of this shall be k delta t. All right. How do you represent a k delta t and a delta t? What one does is, in the form of a picture, you represent this as an arrow, and you simply write 1 here. This 1 represents the area under the curve. It does not represent amplitude of the impulse. It represents the area under the unit impulse. And k delta t you represent by the same arrow. You simply write k, the strength of the impulse, here. We shall consider more properties of the impulse function in the next lecture, and then we shall consider the elementary discrete time signals. We shall have to make distinction between continuous time and discrete time when we consider elementary signals. You will see, for example, that an impulse in the discrete time domain does not go to infinity. It is a finite amplitude. We shall see this in the next lecture. Thank you.